Hello everyone, let's look over chapter 19, aldehydes, ketones, part 2. Next, sulfur nucleophiles. Ketone aldehyde react with thiol. Virtually the same way they react with alcohol to generate thioacetyl cyclic thioacetal. Thioacetal can be converted to alkane, thioacetal to alkane, when react with nickel. This allows for another method for reducing ketone aldehyde to corresponding the alkane. The ketone to alkane. Number 4, hydrogen nucleophiles. Lithium aluminum hydride, sodium borohydride functions as hydride delivery reagents. So lithium aluminum hydride, sodium borohydride. These reductions are carried out under basic conditions. The basic condition, the first step of the mechanism is nucleophilic attack. Nucleophilic attack. Lithium aluminum hydride function as a delivery agent of the hydride ion. As a workup step, acid introduced into reaction flask and alkoxide ion protonated to give alcohol. The reduction of an unsymmetrical ketone forms a new chiral center. You can see the chiral center. You can get the last mixture. So ketone with Grignard reagent to generate methylated alcohol. Also, this one aldehyde with methyl magnesium bromide to generate product. So Grignard reagent attack ketone aldehyde to make an alcohol with a new CC double bond. New CC double bond. Yeah. So recall mechanism of Grignard reagent is constant with the base conditions. So Grignard reagent function as a nucleophile, attack carbonyl groups, forming alkoxide ion. As a workup step, acid introduced into reaction flask, alkoxide ion is protonated to give an alcohol. Okay, cyanide ion, Cn-. Cyanide ion is also carbon-based nucleophile, reversibly added to ketone aldehyde to form cyanohydrin. So on carbon, same carbon, you can see Cn and OH, cyanohydrin. This reaction works better under basic conditions, so catalytic amount of base is usually used. Under base condition, let's check the mechanisms. The cyanide ion function as a nucleophile and attack the carbonyl group. So protonation generates a cyanohydrins. As a workup is not necessary since HCN serves as source of the protons. To achieve base condition, KCN is usually added along with HCN. In this way, there is a more CN minus than H plus. So new chiral center is possible in this direction as well. Now you can see new chiral center. So installation of the cyano group advantages because it can be converted into other function group. Cyano group 2 amine, cyano group 2 carboxylic acid. So ketone aldehyde is converted to alkane, CC double bond, with the formation of the new CC double bond. Okay, next, Wiriga reagent is phosphorus elide. Carbon atom act as nucleophile. Elide, neutral compound, contains negatively charged atom. Against to positively charged heteroatom. Positively charged heteroatom. That's elide. Phosphorus elide. The mechanism is like 2+2 cycle addition between reagent and carbonyl group. Let's check the mechanism. With reagent with carbonyl group. Enough cycle addition. So you can see oxaphosphotan. Oxaphosphotan decomposed to produce alkane and triphenylphosphine oxide. Triphenylphosphine oxide and alkane. So formation of the especially stable triphenylphosphine oxide byproduct drives equilibriums to favor formation of the desired alkene. Given really good reagent, synthesize 2 steps from the corresponding alkyl halide. Triphenylphosphine attack alkyl halide to generate phosphonium salt, and proton transfer step. Finally, you can generate really good reagent. The first step is SN2 substitution. So primary halides are more easily made into really good reagent than secondary halide. So really good reaction is stereoselective, using really good derived from the simple alkyl halide. G alkane is favored. So now you can see same direction for 2 hydrogen, that's G formation. But if with a reagent contains electron withdrawing groups or phenol, so E alkane. So hydrogens, different directions, different location. So E configuration. E alkane is major product. But if vinegar reagent contains electron withdrawing groups, E alkane is a major product. Electron withdrawing group or a phenyl group delocalizes the anionic charge of the Wittig reagent, stabilizing it. So owner Wordsworth's Emmons reaction employs reagents similar to stabilized Wittig reagents, also yield E alkene as a major product. This is a stabilized Wittig reagent. This is resonance stabilized phosphate ester carbanion. This is ester, carb anion, phosphorate. So phosphorate, ester, carb anion. That's HWE reagent. Let's check example of HWE reactions. HWE reagent gives E-alkane as a major product, like a stabilizer with the reaction. Reagent does. So retrosynthesis analysis reveals two possible routes to make given alkane, via with a good reaction. So by using with a good reagent, To determine which route is better, consider alkyl halide needed to make either of these Wittig reagent. Route number 1, you might use methyl halide needed. Route number 2, you might use secondary halide needed. On this carbon, you can see two alkyl groups, secondary halide. Route number 1 is better since SN2 reaction with methyl halide is better than with secondary halide. The overall synthesis of alkane via Wittig reaction. So first, methyl halide with triphenylphosphine. Next, a butyl lithium to generate phosphorus ylide Wittig reagent. Wittig reagent with ketone to generate alkene. Next, let's check Berzelius oxidation. When oxygen is inserted into aldehyde ketone between carbon and neighboring alkyl group. So aldehyde or ketone is converted to carboxylic acid or ester. So the peroxy acid function as a nucleophile and attack carbonyl group. The proton transferred from the one location to another. This state can occur intramolecularly because it would be involved a five-membered transition state. Carbonyl group is reformed with simultaneously migration of the alkyl group to generate ester in this case, and carboxylic acid. Lactones. Cyclic ketone produce lactone. This is lactone. Lactone is cyclic ester. For aldehyde or unsymmetric ketone, layer of the migration is following as hydrogen, tertiary, phenol group, primary, and metal. You have to use this trend to determine radioselectivity. So for example, the ketone liquid for acid to generate the ester, you can add oxygen on this side. This is a methyl group, this one secondary. And then benzaldehyde liquid for acid to generate carboxylic acid. So hydrogen has priority than phenol group. So you can add oxygen on this position. One of these reactions will be needed when carbon skeleton is changed. This is ketone. When you use Grignard reagent, you can add CH3. You can see new CC single bond. And then when you use KCN and HCl, you can add CN triple bond. You can see CC, new CC single bond. And then phosphorus light, you can generate CC double bond. So spectroscopy analysis, IR signals strong peaks for carbonyl stretch. This is saturated ketone, unsaturated ketone. So conjugate carbonyl stretch at a low wave number. Saturated one, 1715, 1680. Increasing ring strain. To the right, increasing ring strain increases the wave number. 1715 to 1780. Aldehydes also gives weak two peaks around 270, 50, and 280, 50 wave number. So when you look at the IR spectrum, aldehyde gives a weak observance around 270, 50, and 280, 50 weak signals for CH stretch in aldehyde. So proton NMR, proton neighboring carbonyl, weakly de-shielded by carbonyl group. So appear +1 part per million downfield. So without carbonyl, you can see this proton around 1.2 ppm. So with next carbonyl, you can see this proton at 2.2 ppm. So aldehyde proton strongly de-shield around the 9 or 10 ppm. So this signals from aldehyde in hydrogen in aldehyde. When you look at the carbon-13 NMR, carbonyl carbon produces a weak signal near 200 ppm. This is a review of the reaction. Thank you for watching Chapter 19, Aldehydes and Ketone Part 2.